In this video, we're going to motivate the importance of computing and computers. Why should you care to learn about how a computer works? Well, computers are basically just number machines. They're very good at doing incredibly fast math. They can process very large amounts of numbers very quickly, which on the face of it might not sound all that interesting. But what makes it interesting is the fact that we store almost all information these days as numbers. This uses something we call encoding. We encode all kinds of information just using different numbers. And that means that the computer can essentially process that information. Let me give you some examples. Every photograph that you've ever taken with your phone is just stored as a series of numbers. In fact, every time you use the word digital, it just means numbers. Numbers are used to represent the information somehow. For every photograph that you've ever taken with a phone or with a digital camera, that image, the picture that you see with your eyes, is broken down into a series of incredibly small squares. And each square is called a picture element, or pixel for short. Each pixel stores the amount and frequency of light coming into the lens of your digital camera or your phone. And each square stores a combination of numbers. They store the amount of red that they receive from the image, the amount of green, and the amount of blue. You might have heard of this as RGB. So for example, a number like 25000, representing the amount of red, green, and blue in a pixel, is a very red color. 02550, on the other hand, on the red, green, blue scale, is a very green color. And when all of the values are high, like 255, 255, 255, that represents white. So what is a pixel? It's simply something that stores the amount of RGB for each one of these tiny squares. And when I say there's a lot of squares, I really mean it. If you have something like a modern iPhone, that's a 12 megapixel camera. Each image that it takes when you use the camera records 4032 pixels in height by 3024 pixels in width, for a total of just over 12 million pixels, hence a 12 megapixel camera. And each one of those pixels is storing the amount of red and green and blue for that tiny little square. If you look at the image on the right, that's the logo, the black and white logo from Wikipedia. And if you looked at it in close-up detail, you could actually see each one of those squares. And each one of those squares is holding the amount of red, the amount of green, and the amount of blue for each one of those pixels. Perhaps interestingly, when those three values are the same, the amount of red, green, and blue is the same, then it shows up to us as on the grayscale. And that's what you can see in that image on the right. If you think about the fact that there are over 12 million pixels for every picture you take with your iPhone, that's a lot of information. And if we wanted to do something like make an individual pixel brighter, then we just have to make the values of the red, green, and blue in that pixel a little bit higher, closer to white. But there are over 12 million of them. So if we wanted to increase the amount of red, green, and blue in every pixel in a picture taken with your iPhone, that's 3 times 12.1 million adjustments, or 36.5 million adjustments for one single picture. That's a lot of work. The principle behind using computers is that we now want to deal with amounts of data where you would not want to do it by hand. And that doesn't just apply to pictures. The same is true of audio or video files. Imagine, for example, your favorite song that you've downloaded from some streaming service. Take, for example, Shake It Off by Taylor Swift. That song is 3 minutes and 39 seconds long. Hopefully you know that when you listen to an audio file, what you hear is an audio wave. But when you download it or when you listen to it over the internet, that song has been digitally encoded, again, representing that audio wave as a series of numbers. Each part of the wave has to be measured and given a value showing whether or not it has a positive or negative value and what the height of the wave is at that point. If you look at the diagram on the right, figure 1 shows us the original wave and figure 2 shows us a series of samples where we take a measurement of that wave every so often. That every so often is important. More samples, more frequently recording the height of the wave means better quality audio. The most common you'll encounter these days is 44.1 kilohertz, which translates to 44,100 samples for every second of audio. So if we think about Shake It Off, that 3-minute and 39-second long song, that's going to contain around 9.5 million samples. Again, that's a lot of data and a lot of information. The same is true of text. If you take a book like Bram Stoker's Dracula, you see that it contains around about 160,000 words. And what you're looking at are a selection of the words taken from one of the chapters in Dracula. What I'm not showing you here is the fact that these words themselves are encoded as numbers. That's how the computer actually stores them. But we're just looking at the text right now because that's easy for us to understand. But even layered on this, if we actually read this text, there are things inside here that we recognize. For example, there are names of people. In red, I've highlighted 2 of them. One, Jonathan Harker, and at the end, Dracula, who may or may not be Jonathan Harker's friend. In blue, I've also highlighted some locations. You might not know necessarily these are locations, some of them you might, but you certainly recognize that they could be locations. This is another level of encoding. It's something that we know about text when we read it. What we could do is we could go through and look at a text like this and look at all instances of people's names and collect information about them. We could even start to track who was talking to who, but that would be a very long and slow process and would require you to read the entire novel. Not that I'm saying that reading Dracula is a bad idea. The good thing is computers can process large amounts of information. The diagram that you're looking at is an abstraction of the interactions in the novel Dracula. By knowing something about who the people are, and we're able to somewhat automatically recognize people, and noticing that they occur next to each other in sentences in the text, we can assume that they're having some sort of an interaction. And this graph is just showing the number of interactions. The stronger or thicker the line connecting 2 of the nodes, when nodes represent people, then the more interaction those 2 characters have. So for example, Mina Harker and Jonathan Harker, who are a married couple, have a large number of interactions. You can start to use these representations to assess what's actually happening in the novel Dracula. And you can also, if you're really paying attention, spot who doesn't really appear very much. This has been filtered so that we have some minimum level of interactions. And what you should notice is that Dracula is missing because actually Dracula doesn't appear very much in the novel. Data is an important facet of why computers have become so important. What we usually find is that data can come in all sorts of forms and from all kinds of places. You might recognize the format of the table on the right as being something you might see on Wikipedia, for example. And this table contains the names and the heights of US presidents. And the really key part about using computers to process data is that it can help us answer questions. So for example, you might have the question, what's the most common height of a US president? A really terrific thing is that computers can go to web pages like Wikipedia and can acquire this data that's in the tabular form on the right relatively easily. One thing that we could do is simply plot the heights of the presidents over time. And that's what this graph shows. On the left are the first presidents of the United States, and on the right are the more recent presidents. And I've also plotted a trend line. So you can see that it seems to be the case that US presidents are getting taller over time. But that wasn't the initial question we started with. The question was, what's the most common height of a US president? And so to determine that, I gathered them together into a histogram. And you can see that quite clearly the most common height of a president is around about 182 centimeters. You're probably wondering what that is in imperial units, and I'll leave that as an exercise for the reader. Data these days is available in all kinds of places. The federal government makes a lot of data available, and I'm going to show you an example using the 2018 crime data that the FBI makes available. They make available this data every year. And the most common way that data is made available these days is in CSV, comma separated value files, the sort of thing that you might recognize you could import into Excel. Excel is a very nice program for working with data, but it doesn't take a lot of data for Excel to really get slow and cumbersome. What you're looking at here are 635 entries that log different crimes on university and college campuses across the United States. And so you'll see columns like what state, what's the name of the college, where's the campus, how many students are enrolled, and then what kind of crimes are recorded for the year 2018. Seeing data like this, it's very hard to get an overall picture of what was actually happening. And again, computers can help us with this by creating visualizations. In this one, I've plotted that data onto a geographic map of the United States, where each state is shown. And I've looked at specifically violent crimes. And in order to make them comparable, I've created another facet of the data, which is how many crimes were there per 1,000 students on a state-by-state basis. And so you get a snapshot of what was happening in a particular year. Social media has been another great source of data as we see more and more people using things like Twitter and posting images and posts to things like Facebook. Here we see social media being represented by Twitter. And I did a search for the latest Omicron variant of the COVID-19 virus. Again, computers make accessing this information relatively straightforward. Here, what I've done is I've downloaded a series of tweets from today that deal with the Omicron virus, and I've tagged them using a sentiment analyzer, something that gives me an impression as to whether or not that tweet is positive or negative in nature. And I'm just showing you some of the tweets, 3 negative ones. For example, there's no reason to believe that Omicron is more dangerous, and positive ones. A well done and thorough look at what we know and don't know about Omicron. We were fortunate to have, and then the tag name of somebody who'd done an analysis. And we can even look at trend data. This is looking at Google Trends for 3 terms: the latest Omicron variant, the Delta variant, and just COVID overall. And we can see what the prevalence of those search terms were. This is looking back over 2 years. So you can see we're pre-pandemic, where COVID really starts to take off. We can see a couple of peaks dealing with the Delta variant, that's the red line. And then we can see right at the end there on the right-hand side, a sudden uptick in this new phrase, Omicron, that most of us probably were not familiar with. And now it's starting to become something that we're all being aware of. COVID, of course, is an interesting example because we've seen lots of uses of COVID data to try and educate the public. There have been many kinds of visualizations and dashboards and projections, but very few of which were actually used or useful. Just as an example, here's one that shows the number of cases from the World Health Organization across the globe. And then here's one just relating to New York, the state of New York. And here's one relating to just Schenectady County. And you can see there's lots of different ways of presenting information, and it's not exactly clear to what extent these are really useful, but they're certainly doing something to inform the members of the public about what's going on with the pandemic. The takeaways from this are the following: that there's all kinds of data and information that are encoded in a way computers can read. We've seen some numeric data, some textual data. We've seen information that we can scrape from the web or from social media. And there's so much information, if you think about how many tweets there were just in the last 24 hours about the Omicron variant, then you don't want to work with that by hand. You really want an automated way of dealing with large amounts of data. And even Excel struggles when we start to deal with very large amounts of data. That data doesn't have to be numbers. So the text example of Dracula or social media, but could also be things like Facebook and LinkedIn and the connectedness between you and the people that you know on those social media platforms. And the key point is that computers can help you process that data to answer questions through analysis and through visualization.